Hey, let's talk about frictional forces and acceleration. This would be section 4D from your Holt physics textbook. 'Tis I, Moser. After this video, you should be able to solve for any variable in a problem involving frictional force. Where the acceleration is not equal to 0. Again, this is section D of chapter 4 in your Holt physics textbook. This is what we're looking at now, folks. Things where the sum of forces on one of those axes is not, in fact, 0. In order to be ready for this, you should already know how to use your coefficients of friction, mu s and mu k, in addition to sums of forces to solve for mass or any variable, any force, when the acceleration is 0. So what are we talking about? So you're already familiar with mu s, the coefficient of static friction, and you know that it's equal to the force of static friction divided by the normal force. It's a ratio of the two. And you know mu k, which is, of course, the ratio. It's the force of kinetic friction divided by the normal force. Again, the ratio of the normal force and force of kinetic friction. Now, in the last section, you used the equations for mu s and mu k along with your sum of forces to find different variables that are in the problem. But in all those cases, on both axes, the sum of forces equaled 0. In other words, these things were either moving at constant velocity or they weren't moving at all. They didn't have any acceleration. And that's what we're going to change up now. So, what should you know? That, hey, you can use a coefficient of friction with all those other variables to find acceleration. You can even use it to find mass. Woohoo! We're going to walk through sample problem 4D together. This is from page 146 in your Holt physics textbook. Let's go. We are told that some kid has a box of books. They attach a rope to it. They pull it with a force of 90 newtons at 30 degrees above the horizontal. I've redrawn the free body diagram for you. We're given the mass of the box of books, 20 kilograms, and the coefficient of kinetic friction between the box and the sidewalk. What's the acceleration of the box? Here's the thing that you need to be aware of immediately, and this is the thing that you put a big gold star next to in your notes. In all of these problems, you have 3 equations to work with. You've got your, in this case, it's kinetic friction, so you've got your mu k equals Fk over Fn. You've got a sum of forces on the y-axis, all the forces up minus all the forces down. In this case, the y-axis is 0. This thing is not levitating up into the air, nor does the problem say that it is sinking down into the earth. But you've got another axis, and the sum of forces on the x-axis has always been equal to mass times acceleration. We just don't always talk about it. But sum of forces on the x here equals ma, and in that case, this equals the applied force on the x-axis minus the force of kinetic friction. Now, it's with these that we're going to start to do substitutions. Remember, we're looking for the acceleration of the box. Since we're looking for the acceleration of the box, and this is just sort of a general rule of thumb, I won't say it's right 100% of the time, but it's a great place to start from. I assume, since I'm looking for the acceleration of the box, that this is the equation that I'm going to want to plug everything else into. So I'm going to need to find expressions that I can use to solve for the things in that equation. Well, the very first thing I realize is I was given the applied force, so solving for the F applied x is easy, but I don't have F of k. So it's a sure bet that I'm going to have to reconfigure some other equation to get my F of k. Well, what would I be able to do that with? This equation. Okay. Now, let's see what that step looks like. Excellent. Mu k Fn equals Fk. Well, does that solve my entire problem? Let's try that substitution. So now I'm showing that mass acceleration equals force applied x minus mu k Fn. Yay! Do I have everything I need? No, of course not. I don't have my normal force. And, you know, if you weren't already cautious, you know to be now, normal force is not always equal to mass gravity. In this case, we do have another force on the y-axis. Let's look at that for a minute. Well, I've got Fn, I've got F applied y. These are both forces upward. And the only downward force is Fg, or mass gravity. So, can I create an expression for normal force? Of course I can. Here I've done it without, with just moving the normal force across the equal sign. But that makes my signs really messy, so I'm going to quickly reverse all the signs here just to make it a little easier to look at. Okay, is that better? Normal force equals F applied y plus Fg. No, I've screwed it up, haven't I? Yes, I have. What's my mistake? I changed the sign on everything but the F applied y. Let me fix that. Whew, is that better? Whose job is it to keep me in line? Okay, so normal force equals mass gravity, or Fg, minus F applied y, which means, of course, that we can take this whole thing and sub it in there. Let's look at what that would look like. Okay, so we have mass acceleration equals force applied x minus mu k times the quantity Fg minus F applied y. And let's just highlight the substitutions that we've done. This entire thing, this entire expression that's highlighted in orange, is a substitution for Fk, force of kinetic friction. And this inner piece in parentheses is a substitution for normal force, which was a part of the expression that we built for Fk. So let's fix up a couple things. I've gone ahead here and substituted F applied cosine theta for my F applied x and F applied sine theta for my F applied y. If we look at the free body diagram, we can see that the x-axis, the force applied on the x, is going to be adjacent to the angle, hence why that gets our cosine, and the force applied on the y is going to be opposite, so that gets our sine. Are we ready to solve for acceleration? Ha! By golly, we are. All right, so I've just brought our equation over from the last slide. I've now divided the entire right side of the equation by mass. And now we're ready to plug in some numbers. So I've got acceleration is equal to the quantity, 90 newtons times cosine 30, minus. Now, note the careful use of parentheses here. The first time I ran these numbers, I screwed it all up because I didn't pay attention to my parentheses and my order of operations was wrong. So I've got in my innermost brackets, mass gravity, 20 kilograms times 9.81 meters per second squared, minus 90 newtons times sine 30. The result of that is multiplied by the mu k, 0.5, and that quantity is subtracted from 90 cosine 30, and the whole bloody mess is divided by 20 kilograms, which gives us 0.11711 blah 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 meters per second squared for our acceleration. Sig figs 2, 0.12 meters per second. Oops, don't forget your squared. All right, that's it. Once you feel comfortable with that, you should be ready to go on to the 4D practice problems. That would be these, and the first two will be your second blizzard bag. Numbers 3 and 4 will be your third blizzard bag, and then we'll do a meetup. Okay, enjoy.